All right. Good morning, good afternoon, good evening, depending on where you are. Welcome to the webinar on ICEG 2021 with the topic 21st Century Challenges in Applied Geophysics. My name is Niels Groby. I'm an affiliated faculty at the University of Hawaii at Manoa, and I will be your moderator for today. Before we dive into this session, let me start with a couple of announcements. And the first of it is that we're all really looking forward to the upcoming 6th ICEG conference on the 25th to 28th of October. So we would like to begin with a small, quick video highlighting the successes of ICEG in the past years up to this current event. All right, that was our promotional video. I hope you enjoyed the growth of our conference in LA. I would like to kindly ask your attention for this copyright notice. So if you can please go ahead and read this. All right, thank you. I would like to emphasize that this webinar serves as an introduction to our conference at the ICEG 2021, which will be fully virtual this year due to the COVID circumstances. The conference will show the latest technological advances in the field of environmental and engineering geophysics. And it will also focus on the bridge between near-surface geophysics and exploration geophysics. So you will see advances in, for example, acquisition technology, active and passive monitoring, UAV geophysics, georesources such as groundwater and geothermal energy, and climate-related geophysics. So please do make sure that you not miss the upcoming ICEG 2021 conference. Also important to know, at the end of today's webinar, there will be the opportunity to join in a speed networking session. You will be randomly placed in a group of 4 people where you have about 5 minutes to chat, get to know each other, exchange thoughts, and just get the feeling of being at the live conference. After those 5 minutes, you will be randomly sorted into a new group of people, and this continues as long as you would like. All right, today's program. We're now in the introduction. After that, there will be 3 presentations of 10 minutes by Dr. Chi-Ping Lim, Dr. David Lunley, and Dr. John Bradford, followed by about 20 minutes panel discussion with question and answer. You can ask your questions at any time in the Q&A. Please do start your question with the name of the speaker to which the question is addressed so that we know whom to address the question to. And at the end of the presentations, I will go through these questions and make sure there's an opportunity for the speakers to answer the questions. All right, the first introduction of our speaker is Dr. Chi-Ping Lim, who is currently a distinguished professor of civil engineering, the dean of the Engineering College, and the director of Disaster Prevention and Water Environment Research Center at the National Yangming Jiaotong University in Taiwan. Dr. Qi Ping received his master's in civil engineering and his master's in electrical and computer engineering and PhD degrees from Purdue University. And his primary research interests are engineering monitoring based on electromagnetic waveguide and developments and applications of near-surface geophysics for solving engineering problems. Our second speaker is Dr. David Lumley from UT Dallas. He's a professor of earth sciences and physics at the University of Texas at Dallas. He's also the Cecil and Ida Green Endowed Chair in Geophysics and the director of the Seismic Imaging and Inversion Lab. David has also held academic positions at Stanford and USC and has served as an advisor to the US National Academy of Sciences. Dr. Lumley has a PhD degree in geophysics from Stanford University, a bachelor's and a master's degrees in geophysics and astronomy at the University of British Columbia, and one of his key primary research interests evolves around 4D time-lapse seismology. Last but not least is Dr. John Bradford, who received a dual bachelor degrees in physics and engineering physics from the University of Kansas. He then received his PhD in geophysics from Rice University in 1991. He served as the director of the Center for Geophysical Investigation of the Shallow Subsurface at Boise State University from 2006 to 2009. In 2017, he moved to the Colorado School of Mines, where he served as the geophysics department head until 2019, the vice provost and dean from 2019 to 2020. And he's currently the vice president for global initiatives and heads the Office of Global Initiatives and Business Development. Dr. Bradford has published on a diverse array of topics that include hydrocarbon detection as both resource and environmental contaminants, geothermal characterization, hydrogeophysics, glaciology, and archaeology. All right. With that, I would like to start today's event with Dr. Qi Ping Lin with his first presentation of 10 minutes. So please do remind to type your questions in the Q&A, starting with the name of the presenter they are addressed at any time. Thank you.
Thank you, Neil. So it's my time, right? Hello, everyone. Today is actually our long holiday, the Mid-Autumn Festival, also called Moon Festival. For those who also celebrate Moon Festival in Asian regions, happy holiday. So I'm Qi Ping Lin. I'm glad to be part of this webinar. In my share of time, I would like to discuss the global standards related to engineering geophysics. So I basically would talk about why we need to standardize engineering geophysical methods and what forms of standards can be defined and how can a standard be developed, what it takes to develop a geophysical method standard. And also I would like to gather current available global standard related to geophysics and give you a basic idea of what is already out there. Okay, so before I jump in, I would like to acknowledge Ron Eberhard and Professor Vincent Dranovich, who answered many of my questions related to ASTM standard and provide me a great deal of information, which is quite useful in this webinar. Okay, so the real motivation behind this panel discussion is really about how we can, because at least I think engineering geophysical method should be used more often in engineering practice. But why is engineering geophysics is still not so widely practiced in engineering application, at least in comparison to biomedical imaging or petroleum geophysics? I think there are some unique features of engineering geophysics methods, engineering geophysical problem. For example, it can involve diverse problems, different kinds of problems, maybe landslide, maybe related to earthquake engineering, pavement, levee, different kinds of problems, hydrogeological investigations. And in comparing to petroleum geophysics, it often requires higher resolution. And we are not looking at interested in only the structural interpretation, but also physical parameters to estimate physical parameters. And engineering problems are often related to public safety. So when it's related to public works, oftentimes we would like to have some sort of a regularization or some specification that we can abide by. Okay, so from my observation, I think the challenges of engineering geophysics can at least include the inherent limitations. For example, the inversion non-uniqueness. There are potential pitfalls in the field conditions where the basic the assumption of a geophysical method may be violated. And also there are limitations on exploration resolution and depth. And a weak link between geophysical and engineering parameters is another main challenge of the use of geophysical method in engineering problems. And so related to the subject of this panel discussion is I think there could be a better initiative of standardization of geophysical methods. So the inherent limitation and the weak link between geophysical and engineering parameters, I think in academic and scientific community, we would do more research to continue to advance the technology. But at the same time, there could be a better and stronger initiative on the standardization. Okay, so before I continue, I would like to do two quick polls, one for geophysicists and another for geophysics, for engineers. For Annika, can you release the poll? For geophysicists, I would like to ask you whether you think geophysical methods can be standardized. So if you are a geophysicist, can you quickly answer yes or no? So if we are done with the first poll, the next poll question is, if you are engineers, do you think geophysical methods should be standardized? Okay, so this should be a yes, just a yes or no question. So I suppose we already have the poll results. Okay, so for geophysicists, the answer, surprisingly, 85% answer yes. And for engineers, 77% answer yes. So I'm glad that we are kind of on pace here because I also heard a lot of different point of view. So let me continue on this. In geotechnical tests, I mean, we're talking about geophysical methods, but if we talk about geotechnical tests, it's often is a well-defined procedure that defines a certain protocol that needs to be strictly followed. So that will produce a final number that can be compared, say, to other numbers that follow the exact same protocol. So geotechnical test is often considered technician work. Okay. And as for geophysical survey, at least for some of the geophysicists I talked to, they consider it's not possible to standardize the geophysical methods because there are many factors affecting the choice of data aggregation and inversion or even interpretation. So different preferences are adopted depending on the expert's scientific judgment. So engineers often consider geophysical methods are quite subjective. And geophysicists often proudly consider the geophysical surveys are professional work. So it's not easy to be standardized. However, the question is, who is a better geophysical expert? So I think the voluntary consensus standards can provide a means for users to give confidence to the user for the intended use of geophysical testing results. And the standard can establish a minimum requirements, for example, data acquisition, data processing. And so that the user that use the data can use their experience and basic confidence of the specification to analyze the data or for data interpretation. Okay, so in a standard, it also gives you a good chance to make clear the application and limitation of a certain geophysical methods. So I think a standard is not necessarily intended to eliminate the judgment and scientific judgment and experience. It actually provides a level playing field for people who would like to use the data. Okay, so from this point perspective, I think the standardization, the development of geophysical standard is actually could serve a good bridge between engineers and geophysicists. The more volunteers that contribute to the development of a standard, the higher the likelihood that the standard will have utility for engineer and geophysical community at large. Okay, so actually, in this presentation, when I talk about standard, I'm mainly referring to ASTM standard, which is ASTM is a very global organization and has lots of standard. And ISO is another one, but I believe that the framework is pretty much similar. It's just that I'm more familiar with the ASTM standard. And for ASTM standard, it has many different forms of standards. So these are summarized in the form of the style. For ASTM standard, we call the Blue Book. So this the standard is a nominal adjective in the ASTM definition. So for the standard, we could have a standard guide. So a standard guide is a compendium of information or series of options that does not recommend a specific course of action. And then after that, there'll be even more specific is the standard practice. So a standard practice is a definitive set of instruction for performing one or more specific operation that does not produce a test results, but is a certain course of action. And finally is the standard test methods, which is a definitive procedure that produce test results. So when I read the Blue Book of ASTM standard, the first question that came to my mind is, if a geophysical survey results is not a test results, then what is it? Okay, so actually the ASTM has a very specific definition of different kind of standard. Okay, so a standard guide, is it actually increases the awareness of information and approaches that in a given subject area. Okay, so it's not a very tight description of a certain method, and so for the practice, it could be the different example of practice. For example, the one that's most related to geophysical methods are the inspection or assessment. Okay, and the test method is actually produce a final number, a testing results for engineers. So maybe I'll be able to elaborate on this a little bit more later on. So now let's move to what it takes to be a standard. Okay, to develop an ASTM standard is an arduous effort. It's a very formidable task. It could take a few years. So it would initiate originate with the ASTM committee. And so, for example, the D18 on soil and rock, which is related to geophysical methods most, and we need to have a technical contact who oversees the drafting of standard, and this person should be a member of the ASTM committee and the subcommittee. So some subcommittee is more focused on the certain perspective of the subject area. So the standard will be initiated, the draft will be initiated by having a subcommittee, a chair to endorse this effort. And then we create a work item. So then the ASTM will set up an ASTM collaboration area. We can involve experts, to have help from knowledgeable others. And So just note that if you have a concern, actually the standard the items to be standardized could also be equipment or technology that are even patented or have copyrighted. Okay, so once the draft is completed, it has to be balloted as some committee member, and every negative vote must be resolved, and the draft must be balloted again at the subcommittee level. And once approved at the subcommittee level, you have to do it again in the main committee level. And again, any negative vote has to be resolved. And if substantial changes are made, the draft has to be balloted again back to the subcommittee committee level, and then back to main committee level. And once approved, it would have a designated number and the year that the method was standardized. And the ASTM standard requires a standard to be fully reviewed and reballot every 5 years. If it's not successfully reballot within 8 years, and then it has to be withdrawn. Okay, so as you can see, the whole process is quite rigorous and takes a lot of effort. So what is currently available in ASTM standard related to geophysical methods? So the main committee related to geophysical methods are the soil and rock. And right now we have 2 subcommittees which has standards related to geophysical methods. The first one is the D18.9. It's the cyclic and dynamic property of soil. And in this subcommittee, we have 2 standard test methods. The only 2 test methods, standardized test methods related to geophysical methods, is a cross-hole seismic testing and downhole seismic testing. Okay, and another subcommittee which has the most geophysical methods standard is the surface and subsurface characterization. So we have 2 standard guides on planning and conducting borehole geophysical logging and surface geophysical methods. And there are a few standard guides on borehole geophysics, including gamma, neutron, EM induction logging, and some standard guides related to surface geophysics, seismic refraction, DC resistivity, GPR, frequency domain EM, time domain EM, and seismic reflection. And please note that most of these standards in this subcommittee were developed originally by a task group whose expense was funded by US EPA grants in the 90s. Remember, at this time, there's a boom of site characterization related to soil and groundwater contamination. This is also an area where near-surface geophysics become becomes a very hot topic and develop all these organizations related to near-surface geophysics methods. But since then, there has been a coherent and strong drive and initiative to continue on the development of these standards. Okay, so in this panel discussion, 4 panel speakers were invited, and each one of them knows very well, well qualified in talking about this subject. And I think they have the first-hand experience from their region. So we have a speaker, Dr. Hadar Baker, who is a professor of applied geophysics in UAE University. He's going to talk about the initiative of Dhabi Emirate in making applied geophysical survey a mandatory requirement for issuing building permits. I think his talk is beyond, even beyond standard, to move to even a regulatory level. I don't think many regions can do that, but certainly this experience will shed some light as how we can continue to drive standardization and even to move the geophysical survey become some sort of a mandatory requirement. And Dr. George Tuckwell, a director of Geoscience and Engineering Division of ICEG Group in UK, will talk about standards in theory and practice. I think he is going to mainly share his experience from the British point of view. And we have Dr. Tomio Inazaki from Japan. He's with the National Institute of Advanced Industrial Science and Technology. And he's going to speak on merits and demerits of making geophysical standards or manuals, the lessons from Japan. And probably many of you already know that Japanese Society of Geological ICEG published a manual of geoengineering and environmental geophysical methods, and he's going to talk about the Japanese experience and the current status of how this manual is used. And finally, Thomas Fechner from Geotomography Germany is going to talk about geophysical standards in Germany and Europe. I think I'm running out of my time, and this is my last slide. Okay, so in this panel discussion, back to the initial motivation is we would like to think how to increase the use of geophysical methods, increase the market for geophysical methods, and in the context of facilitated by the initiative of standardization. Okay, so the current geophysical global standards are mainly used to help guide the selection or location or scope and extend the use of more costly, accurate exploration method like borehole, SPT, CPT, this kind of geotechnical testing. And so the typical purpose is to characterize stratigraphic profile, depth to bedrock, and potential geological hazard. Okay, so I think we can continue to increase the use of geophysical methods in the standardization, but we also can think about how to move towards more direct application. Currently, mostly we just have standard guide. So maybe we can have more standard practice or standard test method that can have a more strict prescription that would encourage or make it more mandatory. And another thing we can think about is right now in the ASTM is only in the Committee on Soil and Rock. And I think we can also move toward infrastructure inspection. Therefore, we can have standard in other subcommittee or committee. For example, pavement, concrete, levee. Okay, so I think there's a more possibility on this. Okay, so this is my my part of a presentation, and I would like to take any question from you later on. Thank you very much.
Thank you, Dr. Chi Ping Ling, for a very inspiring presentation. Lots of food of thought. So please, my question to the audience, if you have any thoughts, questions, place them in the Q&A, and we will come back to them at the end of the presentations. So the next presentation is by Dr. David Lumley from UT Dallas. So David, the floor is yours.
Thank you very much, Niels. Good morning, good afternoon, good evening, wherever you are in the world. Thank you for joining us. I'm going to talk about CO2 monitoring and management panel session that we will have at the conference on October 27th. And in that panel, there will be three of us. Myself, I'll talk about time-lapse monitoring, particular seismology, but a little bit of some other methods too. ZQ Zhu will talk about rock physics and geomechanics. He's from the Wright Research Institute in Japan. And Dave Ponting will talk about reservoir and flow simulation from OpenGeoSim. So I want to start off by just mentioning that we've been injecting CO2 into the earth actually for several decades now, starting with enhanced oil recovery in the mid-1980s. And the reason is when you inject CO2 chemically reacts with oil and also works as a surfactant, and can increase oil production recovery from just, on the order of, let's say, some heavy oils, around 20% recovery up to 80, 90% or higher recovery. I remember us coring reservoir samples after a CO2 flood had gone through, and there was virtually no oil left. Everything had been recovered. So it's a very profitable procedure. The issue is most CO2 for these projects, EOR projects, is purchased. It's not natural, certainly not man-made emissions, and it's very expensive, often food grade CO2. And so because it's very expensive, Most of our monitoring concentrates on making sure this expensive injectant is going where we want it to go. And also we would like to recycle as much CO2 as possible because it's so expensive. And so the goal is not to leave any CO2 in the ground at all, to recycle it. Now, in 2005, the IPCC special report on carbon capture and storage came out, and people really started switching gears and thinking about reducing man-made CO2 emissions. And you may know about the famous wedges, CO2 wedges, the 7 wedges, and carbon sequestration, injecting CO2, man-made CO2 into deep geological formations, is one of the most important wedges. And in that report, it outlines various methodologies where we can store man-made CO2, inject and store it in the earth for very long periods of time, certainly thousands of years, if not more. And so there's been a lot of energy around that. So CCS, carbon capture and storage, is quite different than EOR, has been. And here the goal is to capture man-made CO2 emissions at point sources like fossil fuel burning power plants, cement plants generate immense amount of CO2, agricultural sites, all kinds of industrial sites generate a lot of CO2. So capture it at the point source, compress and liquefy it to a supercritical fluid, and then inject it either into a deep saline aquifer, hypersaline brine aquifer, or into depleted petroleum reservoirs. Now, that is waste disposal, and it's not easy to make money in waste disposal, whereas EOR, of course, is very profitable. CCS is so important, it's been listed in the recent National Academy of Science and Engineering Grand Challenges report. This report identifies a dozen or so technology areas that are major threats to our survival in society if we don't overcome these challenges. And one of the dozen, is specifically mentions carbon sequestration and storage. And of course, there's a huge role for applied geophysics to play here in CO2 storage reservoir exploration, exploring for those reservoirs where we'd inject CO2, then site selection and characterization of the reservoir properties, and then monitoring and verification to make sure that the project is in regulatory compliance. Now, recently, the two have been combined. So we have EOR, or enhanced oil recovery, enhanced gas recovery, and various types of, let's say, uses of CO2 for beneficial purposes. Combine that with the waste disposal aspect of injecting CO2 in the earth to reduce man-made emissions. And that is being called CCUS, carbon capture, use and storage, or utility and storage. And just as I mentioned, it combines CCS and enhanced oil or gas recovery or any other enhancements. And here we might be doing things like producing natural gas that has a high natural CO2 content. Some reservoirs have up to 15% or more natural CO2 in them, stripping off the CO2 and re-injecting it back for enhanced oil or gas recovery. That would be one example. And so this way we have an economic driver for CCS that's not just waste disposal. And you can see the market is really responding to this recently. This is the global carbon market value, just came out, this plot very recently. And just like investment bankers and the stock market trades in energy, they also trade in carbon. And you can see that in the last few years, the carbon market has increased by a factor of 500%. So definitely the investment community thinks that this is going to happen, scale up. So the CO2 monitoring and management life cycle looks something like this. First, we simulate our CO2 injection project. We explore, select, and characterize the reservoir to do that. Next, we start injecting CO2. A commercial CO2 injection project is usually defined as injecting more than 1 million tons of CO2 per year for more than 20 years. Today, we have about 20 commercial projects operating worldwide, and we inject 40 million tons of CO2 per year. And to meet the IPCC goals, we need to be injecting 10 gigatons of CO2 per year, which means we need to scale up all of the worldwide CO2 sequestration by a factor of 250. And if that doesn't sound like a big number, I often ask people, what would you do to increase your salary by a factor of 250? Not so easy. Then next, after we inject CO2, we need to monitor the CO2 both during injection and after injection to make sure the CO2 plume is behaving in accordance with predictions. And the current regulations are requiring between 50 and 100 years of pre and post CO2 injection. Well, that introduces some real technology challenges. How can we monitor in the subsurface for those long time periods, 50 to 100 years? We've never done that before. And of course, once we can monitor and we have simulations and we have monitoring data, we can compare those observations. They won't match perfectly. We'll do model updating to show until we make them match. And then we're in regulatory compliance. And then we continue injecting and go around the loop for the life of the project. So I hope that interests you, and you come and join us on Wednesday, October 27th for the ICEG panel session on CO2 monitoring and management. Thank you very much.
Thank you, Dr. Lumley. You raised some questions for me already, so I will get back to you at the end of this session. And I invite the rest of the audience to do the same. All right, our last speaker today is Dr. John Bradford from Colorado School of Mines. John, the floor is yours.
Everyone for joining us today. I hope that what we're talking about gets you excited for the upcoming conference, and you will join us there. So I'm going to talk about a panel that we've put together on minerals and metals exploration in the Arabian Peninsula. And what I'm going to try to do really is to set this up from a big picture perspective, and why is this so important? And it really comes down to being important because of the energy transition that is underway now and that we're about to really embark on seriously over the next few decades. And the key part of that is that we have a large and growing population expected to reach about 9 billion by 2050. And the energy demand for that large population is enormous. We'd like that future energy state to be sustainable. Our current one is not. And we would like it to have overall positive environmental and social impact. So that's a major challenge. And we'd like to do that while reducing our carbon emissions to a net zero state. As you're probably aware, many corporations and governments have announced a mid-century goal to reach net zero for their energy system. So some of the consequences, if we don't reach that goal, is that the climate will continue to warm, and there will be significant impacts on health, livelihood, food security, water supply, security overall for people, and economic growth. So some fairly serious impacts if we don't manage our carbon more effectively than we have in the past. And this perhaps is one of the greatest challenges we've ever faced, technically and socially both. It's very important though. So the graph over on the right-hand side shows quality of life on the vertical axis, and this quality of life index includes things like infant mortality, access to clean water, total annual income, and average age of death. And the horizontal axis shows energy consumption per person, kilowatts per person. And so you can see that there's a very clear correlation. Increased energy consumption leads to increased quality of life. Ultimately, what we'd like to do is shift that line in the counterclockwise direction, so it requires less energy to have a good quality of life. And we'd like to push the dots up the dots, which represent different countries, up the line so that more people in the world have a better quality of life. So this is an enormous challenge. Geophysics is going to be key to helping solve this challenge, and we need to prepare to make our contributions to that. So I want to come back out here and focus in on this graphic over on the right-hand side. So this graphic really illustrates some of the key things that we have to consider as we go through the energy transition. There's 6 nodes around the outside: oil and gas, which is going to be an important part of our energy mix, critical minerals, which is key, clean water, carbon capture, utilization, and sequestration, which David just spoke about, supply chains, and then advanced energy systems here. What I'm really referring to is primarily renewable energy systems. And then in the inside, we have economics and markets, security, environmental and social issues, and regulation and policy, which makes it all happen. So those things in the center link all these together to help us get to this net zero energy future. All of these things are connected, and if we perturb any one part of this system, we perturb all of these others. So what I'd like to do is talk through just a few of those connections briefly, and then get to the critical minerals piece. So we think about oil and gas. So many of the projections for our future energy mix are anticipating that more than half of our energy supply is still going to be derived from oil and gas or hydrocarbons by mid-century, even as we're aiming to get towards a net zero greenhouse gas emissions by that time. Well, what enables that? The only way that that can happen is with carbon capture, utilization, and storage. And that recent report on CCUS that David mentioned indicated that according to the International Energy Agency, we are not going to be able to get to net zero, or won't be possible to reach net zero without a significant portion of our carbon budget being managed through carbon capture, utilization, sequestration. It's really because it's going to be a challenge to move away from oil and gas while still supplying the energy that the world needs. So that's a key component. Of course, the other 50% of that energy mix will come from what's up in the upper left side, advanced energy systems. Significant amount of that will come from solar and wind, of course, but it also includes things like hydrogen energy systems, geothermal, and other sorts of energy. But as we're building those new energy systems out, that comes at a cost. It certainly doesn't come for free. And the cost in this case is largely from the raw materials that will be required to build both the materials, for example, building solar panels, building coils for wind farms, those raw materials, and building the infrastructure that links all of that into our overall energy grid. So the amount of metals and other raw materials that are going to be required to do that is enormous. Along with that, we have to recognize that we're shifting from one non-renewable energy source, which is fossil fuels, to another, which are the metals and minerals that enable solar and wind and other new energy supplies. So we have to recognize and acknowledge that and be prepared to accept that and the challenges that come along with that. So let's look a little bit about what is anticipated to be the growth in demand for metals and minerals. So I'm showing a few headlines just indicating the growing importance of this sector. Down on the bottom is an example of the metals and minerals life cycle. And so this goes everywhere from exploration, identification of the resources, development, production, manufacturing, distribution, and recycling. And we have to look at that entire system as a whole if we're going to solve our problem. So recycling is an interesting thing, and there's a lot of materials out there that we'll need for the energy future. Certainly, rare earths and other critical minerals can be extracted in recycling, and there's some very interesting, innovative work going on. For example, getting rare earths from recycled hard drives. But the reality is, there just isn't enough of these materials in the existing supply to meet the future demand, and that means that we're going to have to find additional materials in the future to meet that demand. So one of those is lithium. So that's a key one. Annika, could you share the poll? So I've put a question together for everyone here to see what you think about this. And the question really is, how much do you think that the demand for lithium is anticipated to increase between now and 2050? So there's three options there: 50%, 100%, or 1,000%. So go ahead and answer that while I continue to talk, and we'll get to to at least one projection of what that answer is in a few minutes. Start by looking at lithium, a supply and demand curve. This only goes out to 2035, so your answer is not here. So the red curve, this comes from a recent article in The Economist. Red curve shows total anticipated demand that's growing more or less exponentially. And then the bars show the total anticipated supply, and that's growing roughly linearly. And that includes everything from existing operations to ones that are anticipated to come online, includes recycling. And those two start to separate by about 2025. So that sort of poses the challenge that we're facing. It's going to be difficult to meet that demand. And that gap really indicates that we don't know right now how that demand is going to be met. There are some significant challenges there. So lithium is one. This also occurs with base metals. So here's a supply-demand curve similar to the previous one that we saw for copper. And in this plot, the supply of copper is in this projection is anticipated to go down. Right now we're sitting out over on the left-hand side of this wedge, but those two are starting to separate significantly. This is why we've seen record prices for copper recently, and there's a real challenge not only for more exotic things like lithium, but also just for base metals like copper and aluminum. Okay, so it gets us over here. I'd like to see, before I go to the next slide, I want to see the results of the poll. Okay, so almost everyone got it right. So the expectation from this group was 1,000%, and that's pretty close to right. So let's go back and I'll show a curve. Oops, hang on. Let me get back to the slide. Okay. So this is from a recent article in Science, just projecting anticipated demand growth for a whole suite of critical minerals, all the way from lithium to more base metals like copper and aluminum, as I mentioned. And there are some rare earths on here as well. And this is only to supply the materials needed for low carbon energy technology, and doesn't include the needs for building infrastructure to push all of those electrons around. So it's not a full accounting of the increase in demand, but you can see significant demand growth in all of these. So how are we going to do this? This is an enormous challenge. So with that in mind, let's take a look at what's going on in the Middle East. So the map that I've shown over on the right-hand side is only the Arabian Peninsula, but I'm talking about the Middle East in general. And in a USGS open file report back in 2005, they noted that the Middle East hosts a number of the world's great mineral districts, but particularly in the Arabian Peninsula, these mineral deposits are either undeveloped or underdeveloped, and there's great potential there. And so as the demand is growing, this meets the need for countries in this region to diversify their economies and help meet this need that the world has for these materials. In particular, the key metals that are in this region are copper, zinc, iron, and gold, and then a couple of rare earths that are important, niobium and tantalum. So this certainly is an area of growth. Many areas around the world are going to be able to develop these resources, but there are significant challenges that come along with that. And those challenges are the key topic for our upcoming panel. So introducing the panelists. So first is Suleiman Ali Al-Abed Al-Kaabi. So he's an assistant dean for student affairs, associate professor for geosciences, and has been looking at this problem of mineral exploration in the Middle East for a number of years. Jeff Dobrik, he's the USGS Africa and Middle East Science Advisor. And he is going to be talking particularly about how governments can help facilitate exploration and sustainable development of the mineral resources. And then the last, Andres Svedinsky will be our speaker. He and his co-author, Hisham El-Kalioubi, have recently done a review of geophysical exploration for minerals and metals in the Middle East. And he'll be talking about that and some of the specific challenges that are related to geophysical exploration. So it should be a great panel, and I'm looking forward to facilitating that. So that brings me to the end of the presentation. I think we still have a few moments left, and hopefully there's some questions for all of the speakers on the panel at this point.
All right, thanks very much, John. I'd like to invite all the panel members to the stage. There we go. Technology stands for nothing. All right, so we're going to start the Q&A session today. We have about 20 minutes for that. We have a couple of interesting questions already from the audience. Feel free to ask at any time, just starting your question with the name of the speaker. Let me kick this discussion off by having a question to Dr. Chiping Lin. Chiping, you talked about the standardization of geophysical methods. My question would be to you, who should take the lead with respect to conflicts of interest, right? Like if you have a certain commercial procedure, let's say to process seismic data, how do you avoid the commercialism to push the guidelines? And if it's not the industry leading it, who should? So that's a little bit the question.
Okay, Niels, very nice question. Actually, I personally was involved in developing ASTM testing methods. It's a method for, it's actually a patent method with, in my acknowledgement, Professor Vincent Janovich. He was actually my former PhD advisor. He patented this testing methods and had technology transfer to a company. So for ASTM standard, because the rigorous process of ballot and how to address all negative votes, okay? So that part can be well taken care of. So there's no try to avoid patent technology or whatever the personal contact who initiates this standard. Could be a person in a company who could be a person which has the patent, okay? And so in order to invite all the people with the level of knowledge related to the methods, we can form a test group, okay? And all this is done electronically. The ASTM has this very nice online platform for people who can join. All right, and everybody can join the committee, the subcommittee, and so they can take influence in the whole process in the ballots. Okay.
All right.
That answer your question?
Yeah. It does. So there's a protocol for that. That's good to know. All right. My second question would be to Dr. David Lumley. You're talking about CCUS in the context of an ICEG conference, which is focused on engineering geophysics, near-surface geophysics, and of course the bigger energy picture. What is, in your view, the role of near-surface geophysics in the CCUS process?
Yes, thank you, Niels. It's wide open because it hasn't been used too much, and I think there's some big potential here in two areas. So the first is, of course, we inject CO2 in reservoirs that are usually more than 1 kilometer deep, to keep them in the supercritical state. But we're obliged to monitor those reservoirs and make sure there's no leakage, even small amounts of leakage, which could be through caprock, up faults, other ways. And also seepage. There's this concept of leakage, which is man-made in a sense, and seepage, which is natural, and telling the difference between the two. So between that reservoir and the surface, of course, we don't want CO2 to reach the surface if it was to start seeping or leaking. There's the whole overburden, and that is really the realm of near-surface geophysics, depending how you define near surface at different length scales. So if we could help monitor and detect CO2 migration through the overburden, if it was happening, and we have to do that to maintain regulatory compliance, that would be huge. And we'd like to catch it as early as possible before it gets anywhere near the surface, to serve as an early warning system. So that's one big area which will involve, I think, all kinds of near-surface geophysics techniques. The second area is when we use some of our most powerful tools like time-lapse seismology to do time-lapse monitoring of the injection plume itself. There can be a lot of natural changes in the near surface, natural variability over time in terms of groundwater flow and contact, vadose zone changes, all kinds of changes in the near surface physical properties. And those distort our time-lapse images, that non-repeatability. Just like if anybody's ever looked through a telescope and tried to look at magnify a view of the moon, let's say in a telescope, a home telescope, you'll see atmospheric variations will distort your image. And we have the same issue with those near-surface variations distorting our time-lapse images in the reservoir. And so if we could use near-surface time-lapse near-surface geophysics to map and monitor the near-surface changes, we can make deterministic physical corrections to our deeper images and sharpen them up, sometimes by an order of magnitude.
All right, thanks very much.
Mm-hmm.
All right, we have a question from the audience, Dr. Hakim Saibi, directed to John Bradford. John, he asks, I believe that geothermal can play an important role in the energy transition, for example, in the Western Arabian Peninsula. So what is your view on geothermal being an important player in the energy transition?
Yeah, of course, it will be important, and one role that it can play in areas where geothermal is available, and it's not available everywhere, but certainly in some areas it is that it can provide that base load. So one of the problems with solar and wind is that they can be highly variable, and you need something to make up that base load. So geothermal is one possible player in that. And of course, geophysics is quite important in being able to identify and monitor geothermal reservoirs as well. So I think that's important. In the question, he does note geothermal is important in the Arabian Peninsula. I would suggest that solar also can be quite useful in the Arabian Peninsula. So a good question, certainly an important part of the mix, and we will have to pursue multiple parallel routes, including oil and gas with CCUS, to get to our future energy state that everyone is setting goals for.
All right, thank you, John. Dr. Saibi, I hope that answers your question for now. Feel free to follow up if you have any more thoughts on this. We have another question directed to Dr. Chi-Ping Lin, related to the engineering standards. It's a question by Dr. Haidar Baker, who asks, how would you convince the engineers or the geophysicists to eventually adopt the standards?
Well, Well, maybe following the UAE experience to make it in regulatory, top down. Well, mostly for standard is mainly to encourage, and by having a standard is I think is much better than without any standard. And so when I say the development of standardization could serve as a bridge between engineering community and geophysical community, because if we can form some sort of a task force, continue to drive the development of this standard, because the ISO, the ASTM organization, is such a long process, a rigorous process. So when you develop the draft, you will post it on the committee and a subcommittee, and you will receive many comments from the committee members. And I believe when we develop a geophysical method standard, I think the geophysicists will take the lead in drafting this standard. But most committee members in ASTM and ISO are engineers. So through this process, there will be a lot of questions or even negative votes. And when these concerns are addressed, engineers will be somehow more convinced. And once the standard is published, I think it would have a much better influence and penetrate into how engineers perceive the geophysical methods, and they will be more willing to adopt this method in their jobs.
All right, Dr. Lin, there's a follow-up on your answer coming in from Christopher Leach, who asks, how do you address the issue of the cheapest price of operations to be the leading cost, as opposed to the standards made by a group of people and not everyone being present there?
Yeah, I guess this is a question not just for geophysical survey, even for construction business. I'm not sure how to answer this question, to be honest. But I guess it's a little bit beyond the standardization. And at least the standard, by having a standard, there will be certain qualification who those, who are competing the job has to be follow that the certain minimum requirement. But I guess this is also a question for our, I mean, it's a typical question in our engineering industry, and certainly we need to have some sort of a reasonable bidding process to avoid this, a bad competition.
All right, thanks. I think there's a lot of food for thought once we reach that stage. It's good those questions come up already at this point. David, there's another question for you. You talked about 4D time-lapse seismics being a role also for the near surface and getting rid of those distortion effects. How would you rationalize the costs for carrying out such expensive surveys when you're talking about, at this stage, a low profitable operation?
Yeah, well, of course, that the profit, whether it's an expense, a net expense, or profit, depends on whether it's been combined with something else like CCUS. However, that's a great question, and in fact, it's the subject of my talk at the conference, which is we cannot afford to monitor for 50 or 100 years shooting a very expensive 3D seismic survey, 4D seismic survey every year or two or whatever for 100 years. So as a teaser, I don't want to give away the whole talk, but I think we're going to be making a major move from active seismic to passive seismic, and I'll discuss my thoughts on that. That's in the seismic realm. Of course, geophysics is much bigger than seismology, and so there are many geophysical techniques which could be quite useful to monitor a CO2 plume over long periods of time. You don't necessarily have to have super high resolution like seismic can give you. Maybe you just want to see the broad outline of the plume to make sure, and the pressure front, to make sure it's staying within the permitted areas and so forth. And that could involve using lots of other geophysical techniques CO2 tends to be lower density than the water, the formation water, and so gravity monitoring techniques could be useful, even coarse, sparse gravity measurements, time-lapse gravity measurements. CO2 is resistive, and it should be more resistive, for example, than saline aquifers, the brine. And so there's a whole range of techniques that could be deployed, I think, very low cost, in a low cost manner, and sparsely, but continuously recording, almost continuously recording over time, to supplement either expensive high resolution seismic surveys, or, as I'm going to be talking about, real-time passive seismic imaging in the subsurface, which is a research challenge.
All right, thanks, David, for posing this little teaser to your talk. I'm very much looking forward to it. I would like to take this opportunity also to remind the audience that this was an introduction to the panel discussions at the ICEG conference. It's fully virtual, so there's no excuse not to be there, and we will continue diving into these topics. There's another question for John here. John, you showed this deviation of the demand and the supply of critical minerals. The question is, in your view, what is the most important limiting factor for meeting our critical mineral demands?
Yeah, it's tough to pin it down to one, and I would say there are really two primary limiting factors, and maybe they're of equal importance. One is technical, and the mining industry, if you're not familiar with it, is slower than other industries to accept innovation and new technologies. In order to meet the anticipated demand, we're going to have to locate and extract ores that are of lower grade and more difficult to get to than we have in the past. And that's going to require change in practices, adoption of things like machine learning techniques, robotics, automation to enable more efficient recovery of the materials that we'll need. And then I would say on the other side, it's the soft side, which is policy and public opinion that we have to overcome. So currently, to get a new mine online, average globally is about 20 years from discovery to production. Some cases it's 25 or 30 years, which already, even at 20 years, that puts us sort of in the timeline that we're hoping to make this transition. So one, we have to learn a different way of getting that permitting process done more quickly, or we have no hope of meeting the requirements that are laid before us. And that's a big challenge. And part of that is getting society to accept that, they might have to have a mine in their backyard, and nobody really wants that. But nobody wants to continue on the track that we're on. So there's a trade-off there that we have to be willing to accept. And part of that would be doing mining practices differently, so there's less impact on local communities and the environment in the areas around mines.
All right. So when you talk about the public perception, all right, in this thing, we're really focused on the supply, right? How can we improve that? Should there be a change in our human behavior on, our demand side? Should we reduce it? Should we, it's a population growth that's rapid, very rapid. It's the use of all these lithium batteries in everything we do, and we renew our cell phones every year, et cetera, et cetera. It's a little bit off topic maybe, but it's very at the center of the problem, I would say. So what are your thoughts on that?
Yeah, I think that has to be part of it too. So changing things so that we as individuals are less energy intensive, I think that's going to have to be a component of it as well. And maybe that's the biggest challenge. It's hard to get people to change their habits. It's hard to ask people in less developed parts of the world or tell them they can't have the same sort of lifestyle that we have. So it's a tough challenge. We've worked ourselves into a tough spot as a global society, I would say, but some of those things we're going to have to accept. And the energy projection models account for that. So usually if you look at those, there's always a bar. If you look at the carbon management piece, there's always a component of that is energy efficiency and reduced energy intensity, which comes from potentially lifestyle changes, but also technological changes. So.
All right.
Maybe if you don't mind me jumping in here, just the word sustainability, I don't think we've said it yet, but it's actually very important to everything we're all talking about here.
Yeah, agreed.
I love that, and would like to take that as a closing comment for now, David. I would like to warmly thank all our panel members today, Chi Ping, John, and David, for their excellent presentations and a lot of food for thought. I would like to thank all of the audience for being here today, making space in your calendar and sitting behind the screen once more. We really hope you enjoyed it, and we're very much looking forward to seeing you at the conference in the middle of October. All right, with that, I would like to close this session and see you soon.
Thank you, Niels. Thank you, everyone.
Thank you.
Yeah, great.